Hello everyone, I'm Mangfang, currently a master student at Shandong University. I'm very glad to present our work, MHPL, Minimum Happy Points Learning for Active Self-Freedom Adaptation. The topic in our paper is Active Self-Freedom Adaptation, which aims to produce remarkable performance gains with a small set of active target samples. We find the best samples are minimum happy points that satisfy the neighbor chaotic individual difference and the self-discriminant. We propose a novel MHPL framework to explore and exploit the MH points with the neighbor environment, uncertainty, neighbor diversity relaxation, one-shot querying, and neighbor focal loss. Extensive experiments verify that MHPL significantly surpasses state-of-the-art. Recently, self-freedom adaptation aims to transfer knowledge stored in the source model instead of the source domain to the unsupervised target domain. The motivation of our paper is that although existing self-freedom adaptation methods have made some progress, the self-freedom adaptation setting faces a performance bottleneck with limited performance improvements due to the absence of source state and target supervised information. Active self-freedom adaptation can produce remarkable performance gains and break through performance bottlenecks when a small set of information target samples is neighbored by experts. Two factors must be considered to achieve significant performance gains in active self-freedom adaptation. Employing sample size once neighbored will improve accuracy significantly. Employing limited active neighbor targeted well in adaptation. However, the existing method ERPT has yet to achieve these two factors. For one thing, the prediction uncertain is error-prone due to miscalibrated source model and the distribution shift. And the pseudo-neighbor noise on neighbor samples easily influence the effect of standard cross-entropy loss on active samples. In this paper, we find the best samples are minimum happy points that satisfy the following three characteristics. Neighbor chaotic samples refer to uncertain ones with neighbor chaotic neighbors. And taking these samples can get the learning of their confusing neighbors, bring significant performance gains. Individual different samples refer to diverse ones dissimilar to each other in selected uncertain samples. Self-dissimilar samples refer to those that are biased toward the target domain. As shown in the figure, the image points lie mostly in red blocks, and existing active learning methods cannot employ them without method MHPL can. Then we introduce our proposed method MHPL. The framework of MHPL is composed of two components: minimum happy points exploration and minimum happy points exploitation. Next, we detail these two parts. In the minimum happy points exploration model, we first propose neighbor environment uncertainty that is designed to employ neighbor chaotic samples containing the NP and NA. Here, NP describes the chaotic degree of neighbor around a sample, and NA describes how close a sample is to its neighbors. Those with noisy and compact samples tend to be selected. Then, we propose a neighbor diversity relaxation to guarantee individual difference in neighbor chaotic samples. Furthermore, we perform one-shot querying, selecting samples at once according to the row source model, guaranteeing source-dissimilar samples. As shown in the figure, the samples selected by our MHPL lie mostly in red blocks. In the model of minimum happy points exploitation, we proposed a lower neighbor focal loss to make the model focus more on information MH points to ensure the generalization of the target domain. In particular, an F loss assigns a neighbor priority and a nagger weight alpha to the MH points. Meanwhile, the NF loss assigns a smaller weight beta to the rest target samples with pseudo-neighbors. In summary, NF loss is defined as a combination of the above parts. Entropy loss and care divergence are introduced to guarantee them unambiguous and balanced classes. The final optimization goal is stated as: we intensively analyze our method in the experiments on 3 domain adaptation decides: Office 3E, Office Home, and VCDA. As shown from Table 1 to Table 4. Firstly, our method MHPL significantly outperforms existing self-freedom adaptation methods, successfully breaking through the performance bottleneck. Secondly, MHPL can better explore and exploit MH points and maximize the performance gains compared to existing active strategies and ELPT. Finally, it is fascinating that MHPL can outperform all active domain adaptation methods without sensing the source state. We also give an elimination analysis to verify the effectiveness of each component in MHPL. Further, we give other results of the effect of learning, neighbors, loss functions, and the hyperparameter analysis. Additional results on different networks. That's all.